We're going to talk about digital logic today. So this is one of those topics that is probably a little too late in the semester for you to integrate into your robot, but it's something I don't want you to come out of a mechatronics class not having learned about. It is something you can literally go take an entire course about. Okay, in ECE, there's a whole semester-long course called digital logic. So kind of like we did with analog input and sensors on Friday, you're going to get a crash course in this today. Okay, so having taken a programming class, you know the basics of this in code, right? You learned if-else statements a while ago. You know that you can write if x equals 1, and I'm being language agnostic here regarding the syntax, the equal signs and everything. If x equals 1 and y equals 2, then do stuff, whatever the code says, right? You know from a while ago that, okay, for this whole condition to be true, x has to equal 1 and y has to equal 2. And if that's true, then this whole thing in parentheses will be true and it'll do this part of the code, right? Else, if for any other condition, if x equals 1 but y equals 3, or if x equals 0 and y equals 4, right, then that whole condition isn't going to be true and it'll do other stuff. So for this quantity in parentheses to be true, both of those conditions have to be true. And you also probably learned about or, right? So if that was or instead of and, then either one or both of those conditions have to be true for the whole condition to be true. So that shouldn't be a new concept. All we're doing today is doing this, but with hardware instead of code. Okay, we are going to use physical circuit elements called logic gates that accept voltages as their inputs. And as we've mentioned earlier in the semester, I'm kind of going to interchangeably use high, true, 1 in the binary sense, or 5 volts for the Arduino versus low, false, 0, or 0 volts, right? All of these things are sort of equivalent. So today we're talking about circuits that actually accept physical voltages as their inputs and generate physical voltages as their outputs, as opposed to code, where maybe you would use more kind of these first 3 and say if a condition is true. Okay? A simple way that you can build sort of a physical AND function or function is using switches. So if I imagine having a 5 volt supply and I put it in series with 2 switches and then have an LED with a current limiting resistor, right? I'm not going to worry about the value of the resistor. We're not bothering with the math. We can see that LED is only going to turn on if I close both of these switches. Right? So if we say when the switch is closed it is true or high, then that's kind of the physical equivalent of an AND gate, but with switches. And you could also imagine doing that with transistors instead of mechanical switches. Right? So this, if we talk about how these gates are actually constructed internally, it is using transistors, but I'm not going to bother drawing all of that out. We're just going to demonstrate it with switches. So you can also imagine doing that with switches if I put 2 of them in parallel. Right now, only one of those switches has to close for the LED to turn on, right? Or if I close both of them. Okay, so that's kind of a physical OR gate with switches. The motivation for doing this, again, in the context of this class, there's a couple different reasons. One is if you want to build a circuit that has some very simple logic that doesn't actually need any code, right? So you have a motor that you just want to turn on if you press 2 buttons, or a switch that you want to turn on, or a light that you want to turn on if you press one of a multiple set of buttons. Right? Well, okay, you could physically wire it like this, but you could also use the logic gates we're going to talk about in a minute. But that point being, you wouldn't need an Arduino at all. Okay, the logic gates are kind of like a hardware if statement. Another motivation is if you are using an Arduino but want to kind of offload some of the computation because you're running low on pins. Again, say you have 8 buttons. Think of an alarm system, right? We'll get to this when we get to Tinkercad later today. If you have 8 motion sensors and you want your Arduino to trigger an alarm, if any of the sensors detect motion and go high, right? You could do that using 8 different Arduino pins, have each sensor go to 1 pin, or you could combine them through a bunch of OR gates and then just use a single Arduino pin. Okay, if your Arduino is busy doing lots of other stuff and you have a limited number of pins, again, rather than having 8 different interrupt service routines monitoring 8 different pins, you just use OR gates to combine them to a single pin, and then if anything goes high, you just trigger that one single pin. So that's kind of the motivation for why you would care about this in the context of this class. Again, there's 2 weeks left in the competition. Most of you probably aren't going to change your designs dramatically at this point, but if, I believe logic gates are one of the things available kind of for purchase in a lab. If you said, hey, we're running out of pins and we want to use an AND gate or an OR gate or something, you would have that available to you in this class. Okay? Questions so far on kind of background or motivation and stuff? Okay? So what we are going to do is a slightly boring part where I'm just going to write down some of the gates, and then we are going to switch over to Tinkercad. So for each one of these gates that I keep talking about, we are going to have the name of the gate itself, the circuit symbol for it, the Boolean algebra expression, which we aren't really, I've got an L in there, algebra, and then something called a truth table, which you may, have you guys seen truth tables before in a programming class? Okay, good, that's not a new concept. Truth table. Okay. So the very first one is just a buffer. So this does nothing. The symbol is just a triangle, not to be confused with an op-amp, kind of very similar concept to an analog op-amp buffer, but not literally an op-amp. We have an input A and an output C, and it doesn't transform A at all. The output is just equal to the input. And so if we made the truth table, it's just this. If the input is 0, the output is 0. If the input is 1, the output is 1. And again, I'm using logical 1, 0, and 1 here. That doesn't literally mean 1 volt. The actual voltage is going to depend on the logic level of the system you're using. So the Arduino is 5 volts. There are 3.3 volt Arduinos. There are 1.8 volt logic levels out there. Okay, so why would you want one that does nothing? As the name buffer implies, sometimes you might use something like that to protect a microcontroller pin. Okay, so if you have your Arduino pin over here, and there's a bunch of other circuit stuff happening over here, but the stuff over here blows up, then maybe it's just going to destroy your cheap buffer, but not actually damage your microcontroller. So again, no actual logical operation, but you can use it to kind of prevent a more expensive thing from, just like we talked about voltage followers with op-amps, again, very similar concept, even though it's not actually doing logic. But most of the interesting stuff with these gates is all of the following ones that are going to do different logical operations. Okay, after the buffer, we have a NOT gate, also called an inverter, again, kind of conceptually similar to the analog op-amp version, where we have an input A, and the symbol is the triangle with a little circle on the end, which indicates kind of the inversion part. Boolean algebra statement, C equals not A is an A with a bar over it. Okay. Truth table is then the output is the opposite of the input. So when the input is 0, the output is 1. When the input is 1, the output is 0. Okay. 2 simplest gates. Next up, we're going to have the AND gate. So this is the one we were talking about on the previous slide. This one is this little kind of semi-circular dome thing with a flat edge on one side and a rounded edge on the other side. This one has 2 inputs, A and B, output C. The Boolean algebra operator for this is sort of times using a dot. So if you think about the map there, if A and B can be either 1 or 0, and you literally multiply them, then C is only going to be 1 if A and B are both 1, right? If either of these are 0 or both are 0, then C is going to be 0. So this output C is only true if A and B are both high. So that shows up when you do the truth table. ABC. Here we have to go through every possible combination of the inputs. So 0, 0, 0, 1, 1, 0, and 1, 1. And then again for an AND gate, The output is low unless both inputs are high. So the truth table looks like that. And again, I saw enough head nodding that I think this isn't a totally new concept for many of you. Okay? So then we also have the OR gate, which, depending on how bad your handwriting is, you have to be careful not to get mixed up with the and. I'm not drawing this perfectly, but it's pointier, right? It's got a curved left edge and then kind of a point on the right edge instead of just a rounded right edge. Again, inputs A and B, output C. Boolean algebra expression is plus, so C equals A plus B. Or again, if you think of these as ones and zeros and think of anything other than 0 as true, right? That kind of makes sense. So 0 plus 0, C is going to be 0. But if either of those are 1, then C is going to be 1. If they're both 1, then C is 2. But again, we think of anything other than 0 as true, so that still kind of works, right? And I got a little messy with leaving space for my truth tables here. This is kind of shifting down. But again, you go through same combinations of inputs, and then for the OR gate, output is only 0 if both inputs are 0, and then the output is high if either or both inputs are 1. Okay? That is different than from the XOR or exclusive OR gate, which is going to be the same, except it's only true if only one of the inputs is 1 instead of both. Okay, so the symbol has this extra little thingy on the left, A, B, C. Boolean algebra is a plus with a circle around it, so I actually don't know what that operator is called, but I'm not going to worry about it too much. Truth table looks very similar to the OR gate, 0, 0, 0, 0, 1, 1, 0, 1, 1, where the output is only high, and it's exclusive. So if both inputs are 1, then the output is 0. The output's only high if only one of the inputs is 1. Okay? There is about another page worth with 3 or 4 of these, but I think instead of mind-numbingly just standing here and writing them all down while you guys copy them, I will write them into the lecture notes that I'm going to scan and upload, and we're going to switch to Tinkercad now rather than spending another 5 minutes just with me writing down more gates. Okay, so I will leave that there for people to finish copying and for questions, and then we're going to switch over to Tinkercad. Any questions before we switch to Tinkercad? Okay. All right. I also need a second to pull my own Tinkercad. So if you have Tinkercad pulled up already, start a new circuit. All right, add a breadboard. And I did not test this in advance. We are going to gamble. We're just going to use a battery pack for power and hope this doesn't blow up the logic gates. I didn't test what voltage they're rated for. Worst case, we'll just use the Arduino since that gives us an, or we can use the benchtop power supply. For simplicity, add a breadboard and a 4xAA battery pack. Wires nice and color coded. All right. Give everybody a minute to get a circuit open, get that set up. All right. Once you've got that set up, grab a PIR sensor. This stands for passive infrared. So these are the things used in security systems and motion activated lights. Like, I don't know if that's what those little boxes over on the wall are. I can't quite see from here, but any room that you've ever been in where the lights automatically shut off, or like if you're walking around outside at night and security lights go on automatically, that's what these things are. So inside that little plastic dome are 2 infrared sensitive photodetectors. So they detect a differential change between the 2 of them. So it's not just a single detector measuring absolute infrared light. It's looking for something kind of moving across the field of view. We're not going to get too much more into the internals of how they work. But they have this plastic dome on top because they're designed to have a very wide field of view. So you kind of just need one on a wall or a corner to cover the whole room. They have a digital output that's just going to be high if it detects motion and low if it doesn't. So what I haven't tested before is whether you can power these with 6 volts in Tinkercad or not. But if you put one on the breadboard, zoom in and look at signal, power, and ground, you should be able to wire power to your 6 volts, ground there, and if I hit start, is it going to blow it up? No. Okay, so what this does in Tinkercad, it lets you grab it and then kind of move this thing around to simulate motion, and then it lights up these 2 LEDs to indicate that it saw something. So what I'm going to do is just add an external LED to the output. Okay, so there's this signal out pin, and if I put an external LED in series with the output, then when I run it, okay, great. See how the external LED also lights up? Okay, so we got no code running here. This is just a sensor that creates its own digital output when it detects motion. Questions? Everybody good on the Tinkercad part? Okay. So now if you search the part library, maybe I'd have to go to all components first. Or I really thought this is going to royally screw up my lecture if Tinkercad got rid of the logic gates. There we go. No, integrated circuits, optocoupler. There we go, logic. Okay, I don't know why it wasn't coming up when I searched for OR, but if you scroll down, you will see all of these different gates labeled quad. Right, so these are integrated circuit packages that come with multiple gates in a single chip. So actually, I'm going to switch back to the document camera really quick. Draw this, for example, for, I'm going to add a column for IC here and just draw one. You might have something like a quad AND gate where there's power and ground pins, and then A, B, C, individual, this one drew this really small, but I'm going to zoom in there. You have to look up the data sheet for the chip to see what the pinout is, but it'll be something like this, where each set of 3 pins is 2 inputs and then the output for AND gate, but then there will be more of those all within a single chip. Okay, so I'm not going to bother drawing all of those, but that's what we're doing in Tinkercad. Okay, no, laptop. All right, so what I want you to do, grab the quad OR gate. Okay, now again, the nice thing about Tinkercad is you can mouse over to see what the different pins are, right? So we got a ground pin, we got a power pin, and then we input 1B, and output 1, right? So it used a labeling convention a little different than what I did, but there's your 2 inputs, there's your first output, there's your second 2 inputs, there's your second, so you got 4 of these total. Okay, now what I want you to do, rather than me doing this for you, is wire this so there are 4 sensors, and any one of them detecting motion will cause the LED to turn on. Again, think of this like an alarm system, right? You don't care which sensor went off. You just want to set off the alarm if any of the sensors detect motion. Okay, so you've got at least, well, you can add more of these if you need them, but you've got an OR gate integrated circuit that actually has 4 individual OR gates in it, right? And you can add more sensors. Ultimately, I want this LED to turn on if any of the sensors detect motion. Okay? This doesn't actually require an Arduino. You're just doing it with hardware. Okay, I don't quite know how long that's going to take, but we have like 20 minutes left. So give it a shot, and if you have questions, let me know. This thing's good. If it gets too crowded, you don't have to put these things on the breadboard. You can wire them from somewhere else like that. So bare minimum, actually this is another one of the things I probably should have checked to make sure this chip will accept 6 volts as an input, but I think it's fine. Okay. Powering the chip doesn't make it explode. So bare minimum for starters, make sure you power the chip. It has those separate power and ground pins, and then figure out how you're going to wire the OR gates such that that LED will turn on if any of the sensors detect motion. Seeing a lot of green wires, I would recommend color coding. Makes your life a lot easier. Black for ground, red for power, and then green for signal, or different signal color for each of the sensors, whatever you want to do. But if you leave everything green, it gets messy. And don't forget that you can click to route the wires. I saw a lot of straight wires going point to point, so just like keeping things neat is useful with a real circuit, kind of not having the wires all crisscrossing each other and getting super messy can also be useful. So again, minimum, just talking about power, not talking about how we're wiring signals yet. Probably want to make sure all 4 sensors are powered. Yes. Doesn't have power. Well, so you shouldn't need a second chip because you still have other gates unused on that. I also double check. Make sure you mouse over and see which one is in because I don't know. I need to check which. You might have input 1. Okay, no, never mind. You were right. I thought maybe it went counterclockwise where output 3, input 3. Okay, it does go down on the right side like it does on the left. If you have a OR gate output wired to a sensor output, that might be what's causing the short, because they're both trying to act like an output to the other. But maybe that's not how you had it wired, but that's one reason I think could blow it up. Because that way, if the output of OR gate tries to go low and the sensor detects motion and tries to go high, then that's creating a short between high and low. So double check your inputs and outputs. Okay, again, I am not showing how to route the signals yet. I am just going through and getting power connected to everything. Did I hear questions somewhere? Alright, there's power to everything. Thinking of all 4 of them at once is overwhelming. Maybe try just starting with 2 of them. So when you get the LED to light, either of just 2 of them detect motion. Seeing a lot of people with sensors on the screen, but not necessarily a lot of signal wires going anywhere. Think about the sensor signal pin is an output that will be low by default, go high when it detects motion. Think about where you would want that to go with an OR gate. Alright, we got like 10 minutes left. So, if I wanted to do this with just two of them, alright, I could take the output, two of my sensors. Okay, so that's going to input 1A and input 1B. Okay, I got two sensor outputs going to the two inputs of my first OR gate, and then have the output of that gate, which I could send to my LED, which is in series with the resistor. It goes to ground, right? So now I'm not using these bottom two sensors for anything yet, but if I start that, neither of these sensors has detected motion, LED is off. If this one detects motion, LED turns on, or if this one detects motion, LED turns on, okay? Is it clear how I did that with two of them? Okay, because if you don't get how to do it with two, then doing it with all four isn't going to make sense. Okay? So if you were stuck, try to at least get that far, and then see if you can change things such that the LED will turn on if any of the sensors detect motion. Remember, this chip has 4 OR gates in it, so you should not need a second chip. Anyone have it working with all 4? Okay. The wall clock is a little slow. We got like 5 minutes left. I'm going to see if people can get this working without me showing you how to do the last 2. Okay, I'm seeing some thumbs up. Okay. You're still totally stuck. I see another thumbs up. Ask somebody near you, or if you have figured it out and you see somebody near you trying to figure it out, help them out. And I don't want this to just be building Legos where I do it and you guys just follow the instructions. Right? Like, this isn't a super complicated concept, but I want you to at least go through doing it yourself once instead of just copying down what I do, so you understand how to wire these things up if you ever need to use them in the future. There is a process to kind of work backwards if you have some desired Boolean algebra function or result. If you have a giant truth table that has the outputs you want for all possible combinations of inputs, there is a process you can go through to figure out the minimum number of gates you need to accomplish that, which can be important for circuit design where you want to keep things as cheap as possible or have as small of a circuit footprint as possible. We have taught that in this class in previous years. I'm not doing it this year just because, again, towards the end of the semester, it's not something you wind up really needing that practically for your robot project. But again, you can go take an entire class on this if it's something that interests you. Okay, we got 5 minutes left. I'm going to give it another couple minutes, hopefully, for everybody who hasn't gotten this yet to figure it out. But again, maybe as a hint. So you have 2 of these feeding into one gate. I can take the output of one gate and feed it into the input of another gate. Okay, so if, for example, I have my other two sensors and feed them into gate 2 and maybe use a different color. I don't know, I'll make those blue. Okay. So now I have 2 of my sensors going into gate 1, 2 of my sensors going into gate 2. I'll give it a minute, but hopefully you can fill in the blank for what the last thing would be there. I'm actually going to switch over to the document camera for a second. What I guess I didn't say explicitly at the beginning here and was hoping people would figure out is that you can chain these things together, right? So I'll do it with AND gates here. If I have 2 AND gates with 2 inputs like that, I can feed the outputs of these inputs into another AND gate, right? And now this final output will only be high if all 4, so if I have A, B, C, D, and the output E, this output will only be high if all 4 inputs are high. Okay? You can also buy multi-input AND gates that kind of combine all of that into a single package. So rather than having to wire outputs to inputs separately yourself, it's just combined all into one big thing like this, A, B, C, D, E. And then the truth table for that is much larger. I'm not going to draw the whole thing, but you can imagine how it starts out all zeros, goes like this, all the way up to all ones, and then in that case, the output is only going to be 1 if all 4 of the inputs are 1. So I just demonstrated that with AND gates, but basically what I was asking you to do in Tinkercad is to do this with individual OR gates, right? So you chain, you have your 2 inputs to 2 different OR gates, and then you can change the output, chain the output of those 2 OR gates to the inputs of the final one, and then the final one is what controls your LED. Okay, so if I switch back to Tinkercad, okay, I have my 4 sensors going to 4 different inputs total, but I can take, let's see where, I have input 4 over there. I can take the output of this one, go to the input of 4, let's make that green, output 2, go to input 4, make that blue, and then I can take the output for and send that over to my LED. Let's say I'm going to make that orange. Or maybe I'll do that. I'll make all these orange. And now, unless I screwed that up, any of these should cause the LED to turn on. Okay, and all of that is without using an Arduino at all. Okay, the gate sort of just functions as a hardware if statement. Okay, and again, we use the OR gate as an example here, but you could use, there's a whole list of these. Again, I will add more to the written notes. There's about 4 more that are going to be in that big table that I didn't want to spend lecture time on just copying all of them down today. Okay, and again, motivation here, we are using this to turn on an LED, but if you wanted to combine all of these 4 sensors and just feed it to a single Arduino pin, you could do that as well. Okay, so this orange wire would just go over to your Arduino, and then you only need 1 pin change interrupt instead of 4 to detect if any of the sensors went high. Okay, questions? Still 0 questions despite my attempt to motivate more questions at the beginning? Okay, I give up. All right, that is everything for today. Hopefully I will see some of you in lab this afternoon. If not, I'll see you in lecture on Wednesday. Yes?